All right, so we're going to look at an application of Green's theorem to finding areas. Now, in chapter 15, when we talked about double integrals, we showed that anytime you have a double integral over a region D, and your integrand just looks like dA, the result is the area of that region D. But now what we have is a connection between double integrals and the line integrals along the boundary curve of a particular region. So if I want to apply Green's theorem here, what I need, if I'm using a double integral, is one of the form, one that looks like this. The double integral over the region D of the partial of q with respect to x minus the partial of p with respect to y, where p and q are the two variable functions that will appear in a line integral. This needs to be equal to 1 if it's going to simplify to just dA in here. So basically what we're looking for are functions, two variable functions, p and q, such that this holds true. And there's lots of options for p and q that would make this work. For example, if p was equal to 0 and q was equal to x, the partial of q with respect to x would be 1, minus the partial of p with respect to anything would be 0, so that would just be 1. Same with these two functions. If p is equal to negative y and q is equal to 0, you can verify that this equation will be true. Same thing here. If I take the partial of, or if I let p equal negative 1/2 y and q equal 1/2, then the partial of q with respect to x is 1/2. P with respect to y would be negative 1/2. 1/2 minus negative 1/2, which is the subtraction here, would come out to 1. So any pair of these functions will work in Green's theorem to turn this double integral into the line integral that we get in Green's theorem. Remember, the line integral will be of the form p dx plus, plus q dy. So for example here, p dx would be 0, so there's nothing really to write there, plus q dy, that would be x dy. So the line integral of x dy along that curve C, that closed curve that bounds the region D, this would give me the same thing as this, which is an area in this case. These two formulas work as well. So what I'd like to do is an application of this, just showing that this does in fact give us an area that we would expect to see. Now you might look at this and think, why do we need yet another way to determine the area of a plane region? We've been doing areas since the end of Calc 1, where we introduce a definite integral. So what's the point of having even more techniques? Well, this is not the most practical method for finding an area by hand in most cases, but it actually does have an interesting application that your book goes into detail on with a little machine called a planimeter. Basically, the idea is that this area can be computed while only knowing only having information about the boundary curve. So if you look in your book and you look at the part where it talks about this planimeter, it's essentially a machine that traces out a boundary curve and records, using coordinates, where that boundary curve is, and then uses that information with one of these formulas to compute the area of the region that it encloses. So it's kind of an interesting little application of Green's theorem. But for us, we're just going to do one example. What I'd like to do is verify that the area formula for a circle still works with this formula. So here we want to verify that the area of a disk of radius a has an area of pi a squared, and we're going to use Green's theorem. In particular, we're going to use one of those formulas. So the disk can be put anywhere we want to put it, so it makes the most sense to center this disk at the origin, since that's the simplest case. And what I need is parametric equations for this curve C. So the curve C, if it's a circle centered at the origin of radius a, we've seen this before. Its parameterization will be x equals a cosine of t, y equals a sine of t, where t goes from 0 to 2 pi. okay? I'm going to need a dx and a dy in order to use these. So dx is going to be negative a sine of t dt, and dy is going to be a cosine of t dt. So using this third formula right here, 1/2 times the line integral of x dy minus y dx. The area is equal to 1/2 times the line integral along c of x dy minus y dx. Okay, well, x dy, that's a cosine of t times a cosine of t, which is a squared cosine squared of t dt, minus y dx. That would be a sine of t times negative a sine of t. That's negative a squared sine squared of t dt. Notice when I combine these, I'm going to get a squared cosine squared plus a squared sine squared. The cosine squared plus sine squared is equal to 1 after I factor that a squared out. And when the a squared being a constant can even be brought clear out of the integral. So I end up with a squared over 2 times the integral along c of, we did the parameterization, so I should turn this into a definite integral. T goes from 0 to 2 pi here. So I need to make sure and change that into a definite integral, 0 to 2 pi of dt. Okay, well, that's a constant function, and I know that the integral from 0 to 2 pi of dt would just be 2 pi. So I get a squared over 2 times 2 pi, which simplifies to pi a squared, what we would have expected to see, being the area of a disk. Okay, so that's just one application of that. We're not going to do much with that idea, but it's a cool way that Green's theorem can be used. All right, let's start looking at some extended versions of Green's theorem. So all of these extended versions that I'm referring to here are basically taking the types of regions that we were able to prove Green's theorem for, namely simple regions. Remember, those are ones that can be represented as type 1 or type 2, and start extending the theorem to more complicated regions. So what we're going to do is start by looking at regions that can be represented as a union of simple regions. So in this case, we have this kind of peanut-shaped region that we want to use in Green's theorem, and suppose the curve, or suppose the region is not a simple region, but maybe I can split it into two simple regions by putting a line in here. Then I can write D as the union of D1 and D2, where those are the two regions that I've cut this thing into. And then my boundary curve, which I'm going to think of as 3 different curves. So there's the curve here in red surrounding D1. There's the curve here in red surrounding, or at least part of D2. And then there's the line that we put through this region D. I'm going to call that C3. Okay? And remember, in order to use Green's theorem, we have to use a positive orientation for these curves. And this part's really important. When I say C3 in particular, I'm going to be talking about C3 as a part of the curve surrounding D1 with positive orientation. So because we're looking at a positive, which is a counterclockwise orientation, C3 is oriented upwards here. However, if I want to orient the boundary curve for D2 positively, we're going to be traversing C3 in the opposite direction if it's all meant to be counterclockwise. So D2 is surrounded by a boundary curve that includes C2 and negative C3 going the opposite direction. This is really important that we have one going one direction, the other going the opposite direction. Okay, so according to Green's theorem, now D1 and D2 we're going to assume are simple regions, and so we can apply Green's theorem to these separately. The line integral is going to use the boundary curve of D1, which is the union of C1 with C3. That's what we're seeing right here. Okay, and according to Green's theorem, the line integral along that curve of p dx plus q dy is equal to the double integral of the over the region it encloses, which is d1 of this integrand right here. Similarly, if I apply Green's theorem to the second region, d2, the boundary curve for D2 is a union of C2 and negative C3, which is what we're seeing here, okay? That will equal the double integral of the over the region D2 of this integrand. Now what we're going to do is add these two equations and think about what that looks like. This is a line integral of two curves that are that we took the union of. And we know that if I wanted to take this integral, I could represent it as the integral along C1 of my integrand plus the integral along C3 of my integrand, right? I'm not including the integrand in here. I want to keep this relatively simple. If I added this to this and then broke this up into a sum of two parts, this is the integral along C2 plus the integral along the opposite of C3, okay? But here's one thing that we know. If you integrate a function, if you do a line integral along the opposite of a curve, so like negative C3 here, that negative can be brought out here. We've used that multiple times. What that means is that this integral right here, this line integral, is going to cancel this one because it's going to end up being the opposite of this one. So those cancel and leave me with just the union of C1 and C2. The idea is that when you add line integrals of the same integrand, but one of the line integrals traverses part of a curve in one direction, and the other line integral traverses the curve in the opposite direction, these have a canceling effect, just like what we're seeing right here. So that means adding these two line integrals is really giving me the line integral along the curve C1 union C2. Over here, the sum of these two line integrals, because the integrands are the same, double integrals, is the same as the double integral of the region that's the union of D1 and D2. But that was the original region D. So what does all this mean? Well, it shows that Green's theorem applies. This is Green's theorem. Remember, C1 union C2 is the same thing as C, the boundary of D. It applies even in regions that are not necessarily simple, which was the case we were able to prove. In fact, I took that region and cut it up into two simple regions, but as long as a region can be partitioned into any finite union of simple regions, you can apply a similar argument and show that Green's theorem applies for even those more complicated types of regions. We can extend Green's theorem even more to regions that contain holes. Up until this point, we've assumed that the simple regions that we're enclosing with these curves don't include holes. But you can construct a somewhat similar argument, and I'm actually going to kind of just quickly move through this argument so we can get to some more examples. By taking the region D that you're integrating over and cutting it like this. So let's suppose we're dealing with a region with only one hole in it. If we cut this region into two parts with these lines here, then I am basically taking the region D and partitioning it into two regions that I'm going to call D prime and D double prime. And notice if I orient each one of those counterclockwise, then these lines will be traversed towards the right as I circle D prime, and then again towards the left as I circle D double prime. That's going to have a similar canceling effect that we saw in the previous example. So this argument sort of outlines the steps here, but the end result is this, that the double integral over the region D that we originally described up here is equal to the line integral of C. Now in this case, C, the boundary curve, we have to be careful about that. The boundary curve is actually made up of two disjoint curves. So when I say C, I'm talking about the union of C1, this outside curve, and C2, which is the curve that gives us the hole in the middle. And remember, we need this curve to be positively oriented. So the outside curve is going to be oriented counterclockwise because as you move around this curve, D will remain on the left side. But C2 is actually oriented clockwise. And the reason for that is because it's a boundary for the region D, and if you notice, if you walk along this curve clockwise, D will remain to your left. So the two curves are oriented in opposite directions. You have to be careful about that. Okay? So what this does is it means Green's theorem applies to an even wider range of regions that include holes, which we weren't able to consider before. So let's do an example where we're using Green's theorem in such a case. Evaluate this line integral, and this is a complicated looking line integral, and C is going to be the boundary of the region between the circles x squared plus y squared equals 4 and x squared plus y squared equals 9. Okay, so if I were to sketch this region, this is an annulus. Circle of radius 2 and a circle of radius 3 here is what these are describing. I'm going to call this P and call this Q. So Green's theorem says that I can convert this into a double integral, this is the region D, over the region D, of the partial derivative of Q with respect to x. Notice that would be 3x squared. This part of the function here has no x's in it, so it's treated like a constant. So I'm going to have 3x squared minus the partial of p with respect to y, which would be negative 3y squared dA. This is equal to 3 times the double integral over d of x squared plus y squared dA. Now, given the way our region is defined, and given the fact that we have an x squared plus y squared in here, this seems like the perfect candidate for polar. So I'm going to convert to polar to evaluate this, but I want to point something out. I jumped straight into Green's theorem here. I converted this line integral into a double integral. That's what Green's theorem is. I would not have been able to do this if I didn't know that this region, or that we could use Green's theorem over regions that have holes in them. We have a hole right here. Now, one thing that's actually not mentioned here is the orientation of this curve. So we would want to make sure that this was a positively oriented curve, and to show that it's positively oriented, in my example, I'm just going to sketch in this. So notice as I go counterclockwise on the outside curve, but clockwise on the inner curve, that's what gives me the positive orientation that I need. Okay, converting to polar coordinates, this becomes 3 integral from 0 to 2 pi integral from 2 to 3. Remember, this is going to be converted to an r squared, and then dA becomes r dr d theta. So my r squared times that r gives me r cubed dr d theta. And we've done a lot of double integrals with polar coordinates, so hopefully you're comfortable with how I got these limits of integration and all that. Okay, this is equal to 3 times, I can bring the d theta here, and the integral from 0 to 2 pi of d theta would just be 2 pi. And then the antiderivative here for r cubed would be r to the 4th over 4, evaluated from 2 to 3. Just arithmetic from here, this comes out to 195 pi over 3. Or sorry, over 2. Okay. And that's it. So again, Green's theorem looks the same, essentially. I mean, there was a conversion to polar coordinates, but it doesn't look like we've done anything different since extending Green's theorem the way that we did. But really, the extension that we're talking about is just to say that Green's theorem applies in more regions than what we were considering before. Okay, so now what I want to do is take a look at this example. This one's actually in your book. And it's an interesting one. We want to show that if we have this vector field, f of xy equals negative y over x squared plus y squared I, plus this guy here, x over x squared plus y squared j, that the line integral along C of f dot dr is equal to 2 pi for every positively oriented simple closed curve enclosing the origin. That means this C can be any such curve as long as it encloses the origin. So in order to show that, we want to start by letting C be some arbitrary simple closed curve that's positively oriented and encloses the origin like this. Okay. Now, if this theorem is going to be true, and I could treat this like a theorem, then I should be able to find a little tiny circle that surrounds the origin that is also oriented positively, so that it encloses the origin. And I'm going to call that C prime, and that should also have a line integral when I do the line integral of f dot dr over that little C prime right there of 2 pi. Okay, but let's set up the line integral can't find my words right now. Notice if I were to call this region right here D, so basically this line integral, or sorry, this region that's enclosed by C, and then C prime like kind of punches a little hole out of that. If I wanted to find that double integral, or the line integral along that, what I'm looking at is the line integral along C of P dx plus Q dy plus the line integral along negative C prime P dx plus Q dy. Where did the negative C prime come from? Well, because C prime is oriented positively, it's counterclockwise just like C is. But if I want to think of C prime as part of the boundary of this region D, and I want that to be oriented positively, I have to reverse the direction of this so that D remains on the left as we move around this curve. So again, if I'm calling this region D, and I want to use Green's theorem to represent, the double integral and line integral of the boundary curve and region that I'm talking about, the orientation is backwards for C prime. So the negative here fixes that. According to Green's theorem, this would be equal to the double integral over D of this y dA. Now, if you look at what P and Q are, because remember, if you're doing if you're looking at the line integral of f dot dr, it's the same thing as this, px plus qy, where P and Q are the component functions for f. What we end up with here is this. So this will be y squared minus x squared over x squared plus y squared squared, squared all day, minus y squared minus x squared over x squared plus y squared squared dA. You can verify by finding those partial derivatives that that's what this would come out to. Notice that this whole thing is just going to go to 0 because I'm subtracting this term from itself. Okay, so what that means is that the sum of these two line integrals up here is equal to 0. So if I subtracted this one from both sides, I would get this. The line integral of P dx plus Q dy is equal to the line integral along negative C prime px P dx plus Q dy. But this negative and this negative can cancel out. So what this shows is that the line integral, along the general arbitrary curve C, or along the arbitrary curve C, this is the same thing as f dot dr in here, is going to be equal to the line integral of C prime along this little circle right here. Okay, so because this was chosen arbitrarily, any simple closed curve enclosing the origin will have the exact same line integral that this will have. What remains to be shown is that this line integral comes out to 2 pi, and we'll do that part in the next video because I'm realizing I'm running out of time for this one.